Okay, hello. I'm from Goddard Space Flight Center. I've been working as a lead for a NASA laser project from 2008 involving solar wind interactions with the lunar environment, and perhaps not only looking. Say again? Okay. So I'm working on a laser project involving solar wind interactions with the moon, and in terms of a from the moon perspective, perhaps looking back from the moon toward the sun, looking at a mission concept that I will address briefly. As you can see, this is a picture from Clementine of the lunar limb here and the solar corona peeking out around here. It's quite dark in this particular configuration, so it's actually a very nice place to be looking at the solar corona and its structure with the right kind of instrumentation. A problem, I'm from the heliophysics community at Goddard, and of course, we did a roadmap, strategic plan activity a while back, and there's now one going on as we speak. And this view was from there about the fact that with the vision of exploration, the connections between the sun and the Earth and the moon and other planets. And the question now, Quo Vadis, where are we going? Where are you going? What I want to address here in this talk are two topics here: heliophysics, of the moon, the solar wind interaction with the surface of the moon, its atmosphere and so forth, and heliophysics from the moon, using it as a platform for observing other heliophysical objects, of course, including the Earth and its atmosphere and magnetosphere environment is another thing, but in this case, focusing on the sun and the solar corona and all its activity and new ways to do new physics. As part of the decadal survey activity for heliophysics, there was a call for white papers, and also from the planetary decadal survey before that. And so I was, involved. I was a lead on the one about space weathering. So heliophysics of the moon, how the solar wind interacts with the moon, its surface, its atmosphere, what we call space weathering processes, which covers a pretty large range from things like implanting, Harrison-Schmitt's helium-3 on the surface of the moon and how that happens, to production of water, actually all over the surface of the moon, as well as, of course, collecting it in the cold lunar poles, and processing of surfaces, amorphization of rock materials, as they're shown by samples brought back from Apollo. So a whole host of issues there that I'm not going to discuss in detail. We talk about some of these things in the white paper. And then the from the moon aspect, looking at this idea of observing the solar corona, here again shown over here, from lunar orbit, basically doing lunar eclipse observations on a daily basis instead of every few years as we currently do it. This is the project here again, the solar interaction with lunar exosphere and surface that was funded in 2008. So we have three main objectives here. We're trying to define the solar interactions, to characterize the solar wind, from the time of Apollo onward with the available data, which includes Apollo ALSEP data at the surface, upstream monitor data, and hopefully we're going to get orbital data as well from the moon. We actually have that from Explorer 35. So we're incorporating that into a website that I'll mention here briefly called LunaSox, and I'll talk about where that name comes from. Secondly, we're Dr. Alexander Lipatov is doing hybrid kinetic, multi-scale simulations of the solar wind interaction with the moon and its environment. So that's in progress, and we have some initial results that will be reported at a later conference, but I'll just show a snippet of that. Thirdly, we're interested in development of ion mass spectrometer instrumentation for flight on future missions, and then more generally the science of the connection of the sun and the solar wind ions and their charge states, and as they are measured in situ at 1AU and the Earth and at the Moon, perhaps with a lunar mission. So here's our website, which mainly is where you go to look at our data browser services for the lunar data and related data we've been looking at. So it's lunasox.gsfc.nasa.gov for Goddard. We have a number of services over here I'll talk about in a minute. You can see our mascot here is Tom Seaver from the Mets, pitching his winning 1969 World Series game, which coincides, of course, with the beginning of the landed human missions on the moon. Okay, and of course the Mets lose in 1973, and so that's, of course, after Apollo 17. So there's kind of a rough coincidence here, with the history of the Mets, and the human program. So pray for the Mets, if you want humans to return to the moon, please. Okay, so that's kind of one of our little themes here for the website. Over here you'll find various things, news. The data browser will take you to some services which actually allow you to browse and make plots of the Apollo ALSEP solar wind monitor data, also Explorer 35, and we also now have incorporated the data stream from the Artemis P1 and P2 missions, so the solar wind magnetic field and particle data from that, and we get that because we were a part of the Space Physics Data Facility at NASA Goddard, so we're getting that data stream anyway as part of the archival services we provide. And some documents here, those two white papers I just mentioned, will be found here, and other things that we'll be adding in the future. Again, we cover the Apollo ALSEP solar wind monitor data, which the data goes through 76. Those were turned off. 12 was turned off, and all of them in 1977. Again, relating to the history of the World Series and the victory. I guess the Yankees won in 77 or something. So there may be some connection there. So we're providing a range of plotting services for various resolutions of data, 28 seconds to hourly. You can plot frequency distributions and do correlate scatter plots and linear regressions and so forth. So just if your grandma, which is like our grandpa, us, the seniors, and you want to do things in your retirement, these kind of services allow you to do that without having a lot of infrastructure, programmers and stuff, so you can actually look at the data. And looking at Apollo 12 and 15 ALSEP data, one interesting thing, of course, there's at different locations, they have different crustal magnetic fields locally. So Apollo 12 has a stronger, by an order of magnitude, magnetic field there for its span of data. And so if you actually do a plot of, and this is a histogram of frequency of measurements, here, so here's the solar wind speed, so different speeds here and the frequency of those. So the red is Apollo 15, which has the weaker magnetic field, and that has a peak at a somewhat higher speed here. And then the Apollo 12 is actually shifted down to a lower speed. And that would be consistent with a kind of a magnetic shielding effect in a region of higher magnetic field. So if you're grandma and you're looking at this data, you're getting pretty excited. Somebody probably already published on this a long time ago, but it is the kind of thing that you can do very quickly with a browser service like this. I'm certainly going to be looking at this. In terms of future data, various things are going on. They'll be talked about later, I think. So one would be getting the other Apollo data, the magnetometer data from the orbiters, and the surface monitors, and bringing that into accessibility with this kind of system. It's first archived at the Planetary Data System, and then we would sort of provide enhanced access and analysis capabilities for those data through our services. We also have an activity to calculate impact parameters. So if you're interested in the relationship between upstream solar wind monitor data, so here's ACE Advanced Composition Explorer out at the L1 Lagrangian point, and you want to know, how far is it offset, from the moon here at any particular time. So we have a database of calculated offset, or what we call impact parameters for that. So you can sort of pick the upstream monitor that would have the smallest impact parameter and would have the best correlation to the position of the moon at that time to do analysis. Being part of the Space Physics Data Facility, we have other services. One of them is a 4D orbit viewer, meaning 3 dimensions. You can rotate this thing around in 3 dimensions and then follow in time, the position of the moon and other spacecraft. Of course, for example, the Artemis spacecraft would be supported in that, and where they are with respect to magnetosphere, of the Earth back here. So when this thing is out sunward of the magnetosphere, that's obviously a good time to do the solar wind interactions. This is just a snippet of the modeling activity, the hybrid modeling, showing some very interesting structures here, back in the wake region of the moon. This will be talked about at the DPS EPSC meeting in France this fall. So we are making progress on that and looking at the P1 Artemis data, and at those time frames as the starting points for these simulations. And lastly, I just want to focus on the mission idea, which is kind of in an early state. It's been thinking about it a while, but we're sort of looking at whether this is proposable perhaps for an explorer opportunity. And so the idea is that we currently have missions like operating now, like the Solar Heliospheric Observatory, the LASCO instrument, which has various occulters which allow you to look at various regions above the surface of the sun. So here's the sun here, there's an occulter there, and then you see the inner corona here, and then there's another occulter which allows you to look further out at this region here. That the C1 instrument is no longer operating. That has a narrow line resolution. So the science here is looking at narrow, for example, emission lines of iron in the visible to near infrared region. And you need to have very tight resolution to see the lines and not pick up a lot of the background from the other stuff around it. So you want a high resolution spectral imaging spectrometer. But you don't want all this stuff, the problem is when you have an occulter, you get diffraction rings around the edges here, and that degrades your spatial resolution, to some extent your spectral resolution, when things are wavelength dependent. So you get away from that by not needing an occulter. These are solar eclipse observations from the ground. And you're looking through the atmosphere during total eclipse here. This is Shadi Habal's and other people doing these kind of observations. And so you're here. Around the limb here, the sun, the moon, you can see some very fine detail of structure here, and these are the lines, kind of color coded, different lines here, and that relates to how the solar wind is accelerated and heated. And its spatial structure out here, these different colors, and so that relates to charge states of the ions and their temperatures. And those things can also be, of course, observed at the Earth, as they evolve through propagation through the solar wind. So you can also measure in situ at around the moon or the Earth, and connect those two things. And so the concept is doing that with a lunar orbiter, which we might call the Lunar Solar Occultation Explorer, again, LunaSOX. And if we're in lunar orbit, we could be doing these observations with the occultations on the east and west side with respect to the sun, on an hourly to daily basis, depending on the orbit. So this is an example of what you could do in heliophysics from the moon. Certainly, this could be like a LOTI class mission. So certainly, I would support the idea of the lower cost missions to do this sort of thing in that range that could be launched with Falcon 9 or something like that. So I think that would be a really great thing to do. With that, that's the conclusion of the talk. And I think the moon is an exciting place to do physics of the moon and from the moon. Thank you.
Thank you very much. We do have time for one quick question.
Yes.
I was wondering if you have any examples or how your sensors react to high-intensity solar proton events.
Well, if you're doing imaging, of course, you fill up with tracks because the CCDs get zapped by penetrating energetic particles. The energetic particles are a penetrating background if you're doing a measurement, even with a plasma instrument at the moon. If you want to measure those things directly, which is being done by the Crater instrument on LRO, you can do that. So there are many interesting things about high energy particles, including effects on astronauts and health, and space weathering effects on surfaces. Anything more specific than that?
All right. Thank you, John.